Bienvenidos, Hushamdi, and welcome to this HUD 8 networking techtorial on Cisco's Enterprise Networking, Security, and Automation curriculum for CCNA version 7. In this techtorial, we're going to be focusing on Packet Tracer Activity 2.4.11, where we're going to be doing a deep dive and talking about modifying Single-Area OSPFv2. So what are you going to learn about in this video? So in this video, we're going to talk about manipulating the flow of traffic at layer 3 with OSPF. We're going to see two different ways to do that. One with the bandwidth command and the other using the IP OSPF cost command. We're going to talk about why you would not want to use the bandwidth command in certain situations and what the bandwidth command is actually for. We're then going to talk about default settings like the hello interval and the dead interval. We're going to take a look at what Packet Tracer shows us, and then we're going to see what real Cisco iOS is going to show us. We're now going to find out about what types of settings need to match between OSPF neighbors in order for the adjacency to form, and if it's already formed, what settings we need to keep in place so that it doesn't get torn down. So let's dive in to the activity here. So this is activity 2.4.11, where we're going to be modifying Single-Area OSPF. Now, part 1 of this activity asks us to modify the default settings. Now, the two settings it's going to have us change are the hello interval and the dead interval. Remember, on a broadcast multi-access segment like Ethernet, the default values are 10 and 40. So 10 seconds for the hello interval and 40 seconds for the dead interval. So what exactly are these intervals? Well, remember, OSPF is a dynamic routing protocol. And so when we first enable OSPF on the interface of a router, either through the network command or using the IP OSPF, then the OSPF process ID number, followed by the area number in which that interface will participate, when we use either of those two commands, remember, that is when OSPF on that interface will start to send out hello packets. And it's sending these hello packets out to that multicast address 224.0.0.5, trying to discover other OSPF speakers who might become OSPF neighbors. And so on a broadcast multi-access segment like Ethernet, the default is 10 for the hello interval. For the dead interval is the interval at which point we will declare the adjacency to be dead. We can no longer reach our neighbor. And so by default, that value will be 4 times the hello interval. Now, there's some tricky things here that we'll see with Packet Tracer that when you're working with real iOS, you will not see. And I'm going to touch on each of those in turn. So let's follow along with the activity here. Let's go to router number 1 and let's change this default value. Now, how would I see the default? Very simple. Remember, this is a fantastic command to keep in your OSPF toolbox so that when you're looking to see maybe why won't the adjacency come up, or I'm having some issues here and it seems like something's not right, I like the command do show IP OSPF interface and then the interface in question. And so let's check that interface serial 000 because it's going to show us some important information. Here are the timer intervals configured. There is my hello and dead interval, and as we can see on a point-to-point network, the defaults are also 10 and 40. Now, the wait timer has to do with the DR and the BDR election, and so we're not going to talk about that here. This comes up later, and I'll leave the retransmit conversation for later as well as we focus here on those two values. So those are my default values. If I was to say do show run interface serial 000, And actually, we're not allowed to use that command here. So let's just go ahead and say show run. You can see that on this interface, nothing is currently configured. And so they want us to come in and say IP OSPF hello interval. And actually, I apologize. Let me get under the interface, serial 000, IP OSPF hello interval, and we're going to change it to 15. Now, as I do that, I'm going to quickly say do show IP OSPF interface serial 000 because I want you to see what has happened here. We've changed the hello interval to 15. The dead interval still says 40. If I say do show IP OSPF neighbor, you're going to see that there's something different here in these dead timer commands. And take a look at what's happening with our top listing there, and it shows it counting down to 0, and now we receive the syslog notification that the adjacency has gone from full to down with the neighbor out serial interface 000. And the reason that this is happening is because the hello interval must match between the routers. If it doesn't match between the routers, and the adjacency is established, and you change it like I just did, the adjacency will not come up. Or, I'm sorry, the adjacency will go down. If the adjacency is not established, and you set the values manually, the adjacency will not come up. And so let's take a look at what that might look like here on real Cisco routers. All right, so let's jump onto the command line of this 3945E, and let's take a look and see what version of software was it running. Well, we're running a very recent version here. Now, remember, when I refer to real Cisco IOS, I don't mean that as a disparaging comment to what Packet Tracer is capable of. Packet Tracer is an amazing tool, but it is limited in its scope and abilities because it's not the true iOS or the full true iOS operating system. So let's get into global config here on router 1. I'm going to say router OSPF1. Let's say passive interface default, no passive interface, gigabit Ethernet 00. That's the interface that's configured on this router on a multi-access broadcast Ethernet segment. And so now I'm going to go ahead and say network 10.0.0.0, and actually we'll pin it down here with the quad zeros, and I'll say area 0. Now, upon running this command, and let's put the loopback interface in here as well for completeness, upon running this command, I now have the hello protocol, or I should say the hello packets being sent on that interface. So how might I see that? Let's set our router ID as well, and let's make sure we get all of that in there. So how might I see that the hello packets are being sent? Well, I can use a debug IP OSPF hello. Now, what we're going to see here is every 10 seconds being sent to the 224.0.0.5 from this interface 10.0.0.1 are hello packets. Now, remember, it's not going to be exactly 10 seconds, but you can see it's very, very close. What follows after the period there, that's the millisecond timer. So as you can see, it won't always exactly fall at 10, but it's going to be very, very close. So I now have hellos running here. Well, let's say that for whatever reason, I wanted to change the default value. So I'm going to go into interface gigabit Ethernet 00, and I'm going to say IP OSPF hello interval, and I'm going to set that to 15. Let's do the same thing that we did on the Packet Tracer router. And actually, before I do that, let me say do show IP OSPF interface gigabit Ethernet 00 so that we can see the values that we're looking at here. Again, as you can see, those default settings are 10 seconds and 40 seconds. So when I say IP OSPF hello interval, and then I change it to 15, let's rerun that command and let's see what real iOS is going to do. So real iOS is auto-magically going to adjust the dead interval for you to be 4 times the hello interval. So on Packet Tracer, is that what we saw? Let's take a look and say, do show IP OSPF interface. Did Packet Tracer auto-magically adjust that for us? No, it didn't. It left it at the default for a point-to-point interface. The dead interval was left at 40 seconds. And so they're asking us to add this command in here. And again, I can see what they're doing. They want us to enter in both commands so that we can see what happens. But know that on real Cisco iOS, it is automagically going to make the adjustment for you. It's automagically going to change the dead interval to be 4 times the hello interval. Now, what if I didn't want it to be 4 times the hello interval? Could I then come in here and say IP OSPF dead interval, and let's change it to 3 times the hello interval, or 45? What might that look like? So again, I have full control over what these values get set to. But no, if you manipulate the hello interval, iOS, real iOS, will automatically adjust the dead interval to be 4 times that value. And you might be seeing also here that the wait timer is also automagically adjusted to 4 times the hello interval. Now, why might the wait timer be adjusted? So the wait timer is used in the DR/BDR election process. This is the amount of time that a router will wait on that interface, on the segment that that interface is connected to, for a DR/BDR election. And in a broadcast multi-access segment like Ethernet, like this router here, it's going to wait for 45 seconds before it elects itself as the designated router. Now, you'll notice that here it said, the last time we ran the command, it said no designated router on this network. Let's run that command again on this interface. And it was up there above, but I want to run it again to get a clear shot here. So take a look at who the DR is. It's this router. It's router 1 has been elected as the DR because it waited for 45 seconds, or I think when we had initially set it to, what was it, to 15, and it did 4 times to 60, but it's going to wait the wait interval before it says, you know what, hey, I'm not hearing from anybody else out there. I'm going to go ahead and elect myself as the designated router. That's the wait interval. So again, the key takeaway is in Packet Tracer, we're forced to set that dead interval as part of the activity, and the interface doesn't reflect what real iOS will, and that is as soon as I change it to whatever value I choose, the hello interval, the dead interval by default becomes 4 times the hello interval. Now, if I'm not happy with that and I want to adjust that value, I can manually adjust it, and I can make it 3 times the hello interval. Could I make it 2 times the hello interval? And the answer is absolutely. I can make these timer values whatever I would like. Now, here's where I'm going to talk about what the text referenced, and that is, should you be changing these default values? And the answer is, unless you have a very compelling reason to change the defaults are there for a reason. A lot of time and planning, and engineers far smarter than you and I decided that on a broadcast multi-access segment, the defaults will be 10 and 40. On the point-to-point link that we're working with, the defaults will be 10 and 40. And those are the defaults for a reason. And so typically you're not going to change the defaults. Now, I know why the Networking Academy curriculum shows you this, because they're going to ask you about this later on down the road. Maybe you'll see a question that shows the output and the configuration on a specific interface, and then the interface on the other side, that configuration is shown. And the question is, why won't the OSPF adjacency come up? Well, let's take a look at that very briefly as well. And again, I like to segue away here to show you, or to, I guess, kind of go off on a tangent to kind of show you what's really going to happen in the real world and what you're really going to see on Cisco routers. So here's router 2, which also has an interface, 10.0.0.2, in this broadcast multi-access Ethernet segment. And again, they're all just plugged into a switch that's in this, they're all in the same VLAN. So let's say router OSPF2, right? Showing that that process ID does not have to match between OSPF routers. But what does have to match, as we're about to see, are the hello and dead interval. So I'm going to go ahead and say passive interface default, right? A good habit to get into, no passive interface, gigabit Ethernet 00. And then let's go ahead and set our router ID here to 0.0.0.2, something that will never be mistaken for a legitimate IP address. Then let me add in the network command for that 10.0.0.2 interface. And for router 1 and router 2, the area number would have to match. Again, so if you're kind of keeping a list of what needs to match, what might I see in the real world, what might I see on a chapter exam, a quiz, a certification exam, the area number on these interfaces must match for router 1 and router 2 to establish an adjacency. But in addition to that, as you're about to see back over on router 1 where our debug of the hello packets is running, and let's transition back over here, now we're going to see some very interesting information. Now remember, I'm going to turn the debug off now. And the only debug that was running was debug IP OSPF hello, so that we could see the hello packets. Now, this little text right here is very important because this is telling us I've received a hello from the router whose router ID is 0.0.0.2, router 2, that fingerprint for router 2 that uniquely identifies router 2 in the OSPF domain. Now, it says mismatch hello parameters. So if an adjacency isn't coming up, and the first thing that you would check is I would say, well, can I ping, right? Do I have reachability over to router 2? And if that works, this would be the next thing I take a look at. And again, you may go right down to the interface level to take a look at this, or you may kick a debug off. And in the debug, you might see mismatch hello parameters from router 2. Now, what does all of this mean? The R and the C. Well, the dead interval. What is the dead interval I'm currently receiving? And so what I'm receiving from that neighbor, 0.0.0.2, is I'm receiving a hello packet that has a dead interval of 40 in it. What am I configured on my interface? So R is received, C is configured. So the dead interval I'm receiving is 40, but I'm configured for 30. The hello interval, I'm receiving 10, but I'm configured for 15. Now, the subnet mask, these are also values that must match for the adjacency to come up. I'm receiving a /24 subnet mask in dotted decimal notation, 255.255.255.0, and I'm configured for that. But the hello interval and the dead interval don't match. So let's go ahead on router 2 and let's do half of the equation here. Let's go ahead and say IP OSPF, IP OSPF under the interface gigabit Ethernet 00, IP OSPF hello interval, and let's go ahead and set that to 15. But before I do, I'm going to restart my debug. Let's say debug IP OSPF, not packet, sorry, hello. So we're debugging. I'm going to come over to router 2. I'm going to change the hello interval, and let's see what happens here. So you can see that the last received hello packet told us, hey, we've got this mismatch. We're sending hello packets, and that's fine because that's what OSPF does. And we're sending it to the all OSPF routers address, that multicast address 224.0.0.5. So now take a look at what's happening. So we've received the next hello packet. And what do we see here? We made our adjustment. You can see the hello received and configured intervals match. Our subnet masks, subnet mask length matches, but the dead interval still doesn't match. And so the reason that this is important is because not only does the hello interval need to match, Not only does the subnet mask need to match, not only does the area number need to match, but the dead interval must match. So all 4 of those parameters that we just looked at have to match, or else the OSPF adjacency is not going to come up. Excuse me. So let me take a step back here, and now let's go ahead and let's match things up here and say dead interval 30. And basically with these settings, what we're saying is if 2 hellos are missed, then the adjacency, I want it to go down. The dead interval will kick in, and now that all 4 of those settings match, the hello interval, the dead interval, the subnet mask length, the area number, the adjacency transitions from loading to full. And everything looks great. And if I was to say you all to turn my debug off because we're done looking at that, and if I was to say show IP OSPF neighbor, what would I see? I would see that, excuse me, I would see that the adjacency is up. The default priority from our previous packet tracer activity, there is the DR BDR election priority value by default on a multi-access broadcast segment will be 1, and we can see the state. So we are fully adjacent, and who is the DR? Again, this output can be a little tricky, but remember, when you see this, the neighbor ID, that is talking about the neighbor's state. The neighbor is the DR. How else could I confirm that? Show IP OSPF interface Gigabit Ethernet 00. Another great command. This is a great go-to command in your OSPF toolbox. So what do we see here? We see the designated router ID is 0.0.0.1. And that is router 1. I'm sorry, the backup designated, I paused there for a second. I was like, wait a second. The backup designated router is router 1. That's me. I'm on router 1. I apologize. I lost my bearing there for a second. As I looked at that, I was like, wait, I'm on router 1, but that is wrong. So the designated router is router 2, and that's what we see here. And we see the interface address for the DR. Now, let's go a little more advanced here, and let's maybe tangent off a little bit. Why is that important? Well, that information is going to be communicated in the type 2 LSA. We're not to the LSAs yet, but I want to plant that seed. Start thinking about that. Because if I was to say show IP OSPF database, we see this net link state. That's your type 2 LSA, the network link state advertisement. And here's the IP address of the interface of router 2 and the advertising router. So what would that be indicating? Well, remember, the type 2 LSA is going to tell me the IP address of the designated router on that segment. In other words, on this link between router 1 and router 2 that is in a VLAN, a multi-access segment, that is the IP address of the DR. That is the value that the type 2 LSA is communicating, is who is the DR on this link. So again, a quick little tangent there, but something we will be coming back to. So again, we can see here that and let me get it right this time, the DR right there, router 2, the backup designated router, router 1. And so that is what you're going to be seeing on real Cisco IOS. Now let me transition back here because we've changed our hello and dead interval. We've seen, it says after a short period of time. That is the dead interval. That's that short period of time that they're referencing here. When they say a short period of time, it's wherever the dead interval counter was at when it realized the hello interval and the dead interval, those values don't match between router 1 and router 2 anymore. And so once that timer expires, we go from, I'm sorry, not loading to full, we go from full to down. Now, let's go ahead and trace the path, right? So we're done talking about those timer values. Again, a quick recap. They all need to match. Hello interval, dead interval, area number, subnet mask length. Definitely take note of that because you will see that in Cisco exams and quizzes, as well as on the certification side of the house. So now what we're going to be looking at is they want us to, okay, we want to bring the interface back up. So let me make sure I get this correct, because that is going to impact the next step, step number 3. We'll go into global config. And actually, did they want me? Okay, they want me to go to router 2. So let's step over to router 2. We'll go into privilege exec, into global config interface, serial 000. I'm going to say IP OSPF hello interval, and let's match it at 15. But remember, it would still not bring the adjacency back up, or it shouldn't, right? I don't know, packet tracer may not care. But if we said do debug, and let's see if it's even on here, do debug IP OSPF hello. And it doesn't look like it's here. What if I were to go back into privilege exec, debug IP OSPF hello? Now, this would be, it would be nice if we were to see this, right? To have it debug the hello for us. The adjacency wouldn't show me the mismatch. The hello packets, which is where those values are located, that is the debug we would need. So that would be a nice add-on here down the road to see packet tracer allow us to debug the hellos. So let's get into global config, back into interface serial 000, IP OSPF, dead interval, and let's set that at 60. So now we have a match. Now you'll also notice our completion percentage, which I know a lot of viewers are very concerned about, is at 80%, and don't worry, we will be at 100 here shortly. So I've just matched it, but let's say show IP, oh, there we go, OSPF neighbor, and it beat me to the punch. So we've gone from loading to full, show IP OSPF, excuse me, neighbor, and you can see that router 2 now has a full adjacency with both router 1 and router 3. So now what we're going to be talking about, and the chapter did a very good job with this. The chapter quickly called out that you typically don't use the bandwidth when you're trying to manipulate the flow of traffic. And this is a critical takeaway from this section in chapter 2. The bandwidth command should be used if and only if you're trying to adjust the bandwidth setting on the interface to reflect the true speed of the interface. So what do I mean by that? Well, here they have us change the bandwidth setting to 64, and they have us do that only on one side. Now, the reason that they're having us do that is so that they can show us that we can manipulate the flow of traffic. And that statement right there, manipulate the flow of traffic, what that translates to in the real world is layer 3 traffic engineering. That's the term that you're going to hear. So we're going to manipulate the flow of traffic. We're doing layer 3 traffic engineering with OSPF. We're going to change how traffic would normally flow in this environment. And this is a very, very important concept. Now, the way that they have us do it in this activity is using the bandwidth command. I wish that they would have shown us how to do this using the IP OSPF cost command, because they show us that in the reading. They tell us that that's how to do it in the reading, but when we get to the packet tracer activity, they step back and use the bandwidth command. Now, here's the problem with the way they show us how to do it here, is that number one, if that is truly the link of, or the speed of the link between router 1 and router 2, you would do this on both sides of this link. So we would do it on router 1 and we would do it on router 2. Because remember, OSPF is picking the best path based on cost. That OSPF cost value, that by default is the sum of all of the outgoing interfaces. And let me change this to red here. It's the sum of all of the outgoing interfaces on the way to your destination. So let's take a deeper dive look here and let's truly understand what it is they're asking us to do and why we're seeing what we're going to see. So I'm going to go back to router 1 because that's the router on which we're going to be making the change. If I say show IP route, let's take a look at the values we have here. Now, they want us to trace out to that internet web server. So let's go ahead and say trace to the 64.100.1.2. And hopefully we're going to keep all of this in the same frame here. And we are. Now, when I look in my routing table here, when I said show IP route right up here, do I have a specific route to get to the 64.100.1.2? Is there any specific route in my routing table that's going to get me there? And the answer to the question is no. So if I don't have a longer, more specific match, and when I say longer, I'm talking about the subnet mask length. So do I have a longer, more specific match to get there in any of those entries? And the answer is no. But what do we have? And we'll be covering this in the next packet tracer activity. What I do have here is I have a default route that is being advertised from router 2. And router 2 has the internet connection, right? So that's the router that would be advertising the default. And so what this is saying to me, this routing table, in English, when I look at this routing table is, hey, if you want to get to any of these specific networks here, then these are the interfaces out which you would go to get there. But if you don't have a specific match for traffic that you're receiving when you do your lookup and you look at that destination IP address in the IPv4 header, and you don't have a longer, more specific match to get to that destination, in our case, the 64.100.1.2, then use the default route. And right now, we're learning the default route, and we're being told that the best path for the default route is out the serial interface 000. And the trace route proves this. My first hop is to the 172.16.3.2. And that is router 2's address. Let's come over to router 2 and let's say show IP interface brief. That is router 2's interface, 172.16.3.2. So we're learning the default route from router 2. And that is my best hop to get there. And you can see that the cost is 1. So here's what we're going to do. And this is what the activity is trying to get us to. It's showing us that, hey, you can throttle down the bandwidth setting on this interface to make it look less attractive, to make the default route look more attractive coming this direction, then going that direction. And that might be the case, because if this link between router 1 and router 2 is truly only capable of 64 kilobits per second, that is terrible with respect to speed in today's networks. But if that's what that link is truly capable of doing, maybe this is a full T1, and maybe this is a full DS3. Those would be more preferable than going over 64 kilobits per second. And again, to refresh, and if this is 64 kilobits a second, which was what we're getting ready to set it to, and this is 1.544 megabits per second, we're saying that this is a full T1, and we'll say that this is a T1 over here, and I'll just write T1 for brevity. But if these are both T1s, then would I want to go 64 kilobits a second or 1.544, 1.544? And that answer should be abundantly obvious as to which direction you want your traffic to flow. So let's say that that's the scenario. So back over on router 1, let me make this change over here and get into global config and get into interface serial 000. Now remember, we've seen the cost going to router 2. We see that that is the preferred path. But when I get into the interface, and before I change it, do show IP interface, not IP OSPF interface, but do show IP interface serial 00, excuse me, I'm sorry, do show interface serial 00. I put the IP in there, I apologize. So this is where we would see what exactly is the interface capable of right now before I make the change. And you can see it reflects it's a T1. So maybe we have a fractional T1 from our service provider, and this happens. Your link speed could be 128 kilobits a second. It could be 256K. It could be 512K, 768K. It all depends on how you've got it carved up, right? Now, a full T1 is 1.544. Here, what we're saying is bandwidth 64. Now, if you were looking for the 100%, you can see the completion percentage is at 100, but there's much more important information that's about to follow here. So, I've changed the setting so that it reflects that this interface, which we saw here a minute ago, was saying that it was capable of 1.544 megabits per second, or 1,544 kilobits per second. We've now downshifted and made this interface appear in the OSPF calculation for cost. We've made this interface look worse than a full T1 at 1.544. So now in the routing table, what are we going to see when I say show IP route? Well, what we're going to see here is now we prefer going out serial 001 over to router 3. And that's the path we would take. Now, if in fact this link is truly 64 kilobits a second, you would not leave the bandwidth setting at 1.544 on router 2. You would come into router 2, you would go into global config, interface serial 000, and you would say bandwidth 64 so that it matches. Because you want your traffic to flow both egress, and egress means outbound, and ingress, which means inbound, and we're talking about from router 1's perspective, I want the traffic leaving my network and then coming back to me. I want it to follow the same path. And when it doesn't do that, we refer to that as asymmetric routing, which would be the traffic from PC1 goes out the path we want it to go out, and it gets to the web server, right? And so we make it to the web server, but then the return traffic comes back to router 2, who on this interface thinks it's still a T1, and that could be the preferred path, and then comes back this way. And so it's like we do a loop, a circle, if you will, right? It's not symmetrical. Now, asymmetric traffic is not the end of the world, and it's not always a negative thing. But typically, best practices, we try to avoid asymmetric traffic when we can. We want a symmetrical traffic flow, something predictable that I know if it's going to go out router 1 to router 3 to router 2 and into the web server, it's going to come back that same path. And so that's what I would do, is set it like that right there. Because if that link is 64 kilobits a second, then both sides of that link should reflect the true bandwidth of the interface. And that's what I'm going to close out with on this activity. Is what I'm going to say is you would not use the bandwidth to change the bandwidth on the interface. Let me rephrase that. You would not manipulate the bandwidth unless you're doing it to accurately reflect what that interface is truly capable of doing. And so here, if it's only 64 kilobits a second, then this is exactly what you would do. If it's not 64 kilobits a second and it's a full T1, that is not what you would do. In fact, let me show you how you would handle this. So I'm going to say no bandwidth 64 on router 2. I'm going to come over to router 1 and go back into global config, back into interface serial 00, and I'm going to say no bandwidth 64. Right? So now we've set it back. Now the completion percentage has dropped off to 80, and that's fine. We already know how to get to the 100. But again, like I always say, it's not about the 100%, right? This is what it's about. It's about understanding how to truly perform layer 3 traffic engineering and knowing when you set the bandwidth and when you don't. So let's say that that link between router 1 and router 2 is a T1, and it is capable of 1.544 megabits per second. You would not go in and manipulate the bandwidth in that instance. You would leave it the way it is. So then that begs the question, well, how would I change the traffic flow? You would use the IP OSPF cost command. And I'm hoping that Packet Tracer is going to cooperate with me here on this. And again, we may end up with an unexpected result. And okay, good. So it does support this command. So what I'm doing now is on this interface here, I'm going to set the OSPF cost to look terrible, much worse than the cost of that interface, serial 001. And so here's how you would do that. I would simply come in and I can pick an arbitrary value. It just has to look worse than serial 001 is going to look. So I'm going to say IP OSPF cost 65,000, right? Now the maximum is 65,535 for the individual interface setting, but that's a pretty terrible value. So now let's say do show IP route, and as you can see, we now prefer the path out serial 001. And again, if I was to take that command off, and I think I forgot to do that earlier, and then say do show IP route, and it doesn't look like it's going to come back here. And this is a packet tracer. There we go. Okay, good. I was waiting for packet tracer to sort itself out. So you can see, right? So again, I'm showing you the proof is right here on the CLI. Right now, the preferred path for the default route is out serial 000. I drop in the IP OSPF cost command, making that path look terrible from an OSPF perspective. Oops, sorry. From an OSPF perspective, and now I'm going out serial 001. But again, I would want to come to router 2 and say IP OSPF cost 65000. Now, I'm using a very high value there. Typically, that's not what you would use, but again, I'm trying to demonstrate demonstrably that, you know, these high values, that's definitely going to shift your traffic flow. This is how you would perform layer 3 traffic engineering. Again, remember, the bandwidth command is there so that you can accurately reflect the speed of the interface. If the interface speed isn't inaccurate and it's not wrong, then you wouldn't put that bandwidth command in there to do OSPF layer 3 traffic engineering. You would use the IP OSPF cost command. Now, last thing I'm going to say here, why would you not change the bandwidth command? If it doesn't need to be changed, why would you not go in and use the bandwidth command? And the answer is very simple, and I want you to give this some thought. What if we were running EIGRP in this network as well? What if I had quality of service running in this network? What might happen? So if you change the bandwidth using that bandwidth command and you've got QoS running, you now may end up with unexpected and inaccurate QoS results. If you're running EIGRP, which uses bandwidth and delay by default, the K1 and K3 composite metric values, you've now maybe just changed how traffic is going to flow with EIGRP. And again, maybe that's what you wanted, but maybe it's not what you wanted. So that is why the bandwidth command should not be used unless you're putting it on the interface to accurately reflect the speed that that interface is operating at. All right, well, that is all I've got for this activity. Again, we've covered a ton of ground here. I hope that this has really clarified a number of things for you. Some default settings that you definitely need to be aware of. The area number has to match. The hello interval has to match. The dead interval has to match. The what else did we say? I think we said something else. There's one that I'm missing. It's going to come to me in a second. So those 3 things need to match. There's a 4th that I'm just losing it right now in terms of what that 4th is. But then we looked at layer 3 traffic engineering, right? How do we shift the flow of traffic? They showed you how to use the bandwidth command, but again, only do that if that is the real speed of that interface. If it's not, you're going to use IP OSPF cost. And I wish that they would have changed that in this activity. So again, let me repeat one more time. The 4 things that need to match. The area number needs to match. The subnet mask length needs to match on those interfaces. That was the one I was forgetting. I apologize. The hello interval and the dead interval. Again, I appreciate your time. I hope I've earned your time, and I hope this has really helped you understand these concepts with OSPF. Thank you so much for watching. Have a great holidays, and I hope to see you in the next video.